Right. All right, welcome everybody. Today we'll be hosting our datasheet workshop. My name is Gerardo Sanchez. I am the IEEE free mentor, but today I'm here to present to you just a quick datasheet workshop. So just to start off, what is a datasheet? Datasheets are basically just instruction manuals for electrical components. They typically just explain what the component does and how it behaves and how you can actually use it. Starting off, datasheets can be pretty difficult to read, I'd say. They might seem pretty overwhelming at first glance, especially for beginners. But once you get used to it and you know what you should be looking for, they're like a really useful tool that you can use. And again, they're still the best place to find certain details that you need when designing a circuit and knowing how to use a specific component. So typically, we're just going to be going, I guess, on the different pages that you'd find on a data sheet, different things that you can see. One of the first things is typically just a summary, and it's typically just the first page of your data sheet. And on your summary, you can just quickly find a description of the part's functionality. So you just find a general description on the component itself. You can see some basic specifications on the component, some of its features, and some of the applications that you can have for this specific component. And just quickly reading through the summary for a specific component, whichever one it is that you're searching up, it can quickly indicate whether this specific part that you're looking at will be well suited for your project, whether it be just a simple lab or it be a project for like a design class or something. And here on the right is just an example, like a picture for a L555 timer. This is this data sheet's summary page. So you can see you have some features, applications, a general description, and some information on different packages and body sizes, and just even a quick schematic of the inner workings of the specific chip. One of the next things that you'll see on a data sheet typically is a pinout. If it is an integrated circuit like the ones on the right, if it's just a diode or a transistor or something like that, you might not see such an extensive pinout. But the pinout lists the pins and functions and the locations, and they're going to differ for different packages. So on the right, you can see the one on the top is the one that you'll typically use in classes, if anything, and it's just a 14 pin. This is the one that you'll typically use with like a breadboard or something. And the one on the bottom is a different package which can be used for different applications, but it's still the same chip and the same functionality. So on the pinouts, there are special indicators to determine where your pin 1 is. And then pins are typically numbered starting at pin 1 and then kind of going counterclockwise around the chip. So for the top one here, this is just, like I said, just like a regular IC chip that you typically see. And you have this little indentation or notch at the top of the chip. And then to the left of that, the first pin to the left of that is typically just your first pin, pin number 1. And they're numerated in a kind of counterclockwise order up until you get to 14. And now each one of these pins are typically labeled with acronyms, some of them being VCC, which is your power, GND, which is your ground. Some other things you can see is CLK and CLR, which is just your clock and your clear. And but in this case, we can see that this one has an input like 1A, 1B, and 1Y. And those are just like 2 inputs and then a single output. This is for a quadruple 2 input positive AND gate that we're looking at here on the top right. So you just have four AND gates in there with 2 inputs for each and 4 outputs and 1 output for each. So you're gonna have, what is it, 8 inputs total and then 4 outputs. And another thing about pinouts to note is that a star next to the name or a line over a specific name typically indicates that a pin is in an active low state. Yeah, and then so another different kind of pinout that we see here is for an LM741 amplifier. And this is going to have different acronyms. Well, not really acronyms, but just different names to the different pins. So pin 1, you have offset null. Pin 2, you have your inverting input. Pin 3 is your non-inverting input. And pin 4 is your negative voltage. Pin 5 is your other offset null. Pin 6 is your output. 7 is your positive voltage, typically like plus or minus 15 volts there. And yeah, and then you can see again, this has 2 different packages, which is another thing that we'll be going over later. So the next thing that you typically see in a data sheet is the absolute max ratings. These are the electrical specifications a part can withstand before damaging occurs. One important thing to note is that you should never exceed these limits or these ratings at all. And these are not the max operating limits that you should be running at either way. So once you get to these operating limits is basically at the point where you can say you fried your chip or you blew up your diode or your LED or something like that. So that's typically, you want to stay as far away from these ratings as you can, just to not mess up any components that you have. So on the bottom left here, we can see that this is for a diode. And you can see that your max value for a reverse voltage would be right here, 75 volts. And your peak forward surge current should be about 2 amps. Anything here is like, if you're operating at about these specifications, you're basically broke the diode, I would say. And then the one on the right here are the max ratings for a PNP silicon transistor. So right here, you can see that the collector and emitter voltage, your max should be about 50 volts DC. And then for your base voltage, collector base voltage, your VCB is about 40 volts DC. And another thing before we move on, typically the charts that you'll see on data sheets are typically separated like this. So you'll have the rating or just the name of whatever parameter it is that you're looking at. Your symbol, which is just like its value name. So here we have voltage of collector emitter. So this is just VCE out. And then right here we have our voltage for the baseline collector. So we have VCB out. Then you have your values here and your units at where you're looking at. So here we have voltage, and then we have amperage, and then here we have watts, and so on and so forth. So one of the next things that you'll see on your data sheet is your recommended operating conditions. This is typically where you want your component to actually be working at. And this includes voltage and current ranges for various different functions. You can also see some timing information and as well as some temperature ranges for which your component should be operating at. And even this recommended operating conditions can contain tips for proper functionality, which can help when you're debugging. So for example, here on the right, we have a single 2-input NAND gate with an open drain output. And this is kind of something that you might be working with, let's say in your 201 class, where you're using these IC chips with logic gates in them. And like I said, they can contain useful tips. So if you see here at the bottom, it says that all unused inputs of the device must be held at VCC or ground to ensure proper device operation. So sometimes if you're getting like really funky outputs and stuff that you're not supposed to be getting, just reading up on the tips that the data sheet gives you can help you find where your error might be coming from in your circuit and stuff. But in terms of the recommended operating conditions, you can see here that it's recommended for your supply voltage to be, if it's in operating, to be at about a minimum of 1.65 volts and a max of 5.5 volts. And again, right here, it's telling you about how much voltage your high input should be at, and for your low level as well. And then this would be, if you're putting in quote unquote zeros or ones or higher lows into your logical chips, this is where you want your voltage to be around just to get those proper ratings. And then same for here at the bottom, this is again, just trying to show as many examples as I can. This would be for that operational amplifier that we saw previously. So your supply voltage would have to be minimum 10 volts and then plus or minus 10 volts. max plus or minus like 22 volts. And then you have your normal right here, which like I mentioned is typically like your plus or minus 15 volts for your supply voltage for your operational amplifiers to be turned on. And then even here, you can see that we have some temperature ranges, which is -65 to 125 degrees Celsius. And again, this is kind of the range that you want your operational amplifier to be working at. You don't want to get too hot, or if it's too cold, it might not function. So next up in data sheets, you might see some graphs, and graphs typically describe characteristics that can't be captured easily just on tables. Typically what they depict is a part's performance versus various criteria. And this can range from your supply voltage, your current source, and even contain different operating temperatures at times as well. So here on the right, we have that fast switching diode once again, and these are the typical characteristics in graphs that you might not be able to be so easily described just on a single table. So here on the top left, we can see that we have a forward voltage versus our junction temperature. So on the y-axis, we have our voltage and how it reacts to certain junction temperatures in degrees Celsius. And then we have our reverse current versus our reverse voltage here on the right. And then here on the bottom left, we would have our forward current versus our forward voltage. So yeah, this is where you typically find just useful graphs. This is kind of something that you might be seeing in like EE 330 probably, where you start learning about diodes and transistors. Typically, you'll see a lot more of these graphs for characteristics when it involves those kinds of components. Up next, this is probably only applicable to like logic gates. You'll be seeing like truth tables, which describes the changing inputs and its effect on the output of like, let's say how we saw the pinouts. You can see how the changing inputs into your input pins can affect your output. And each line has its own input set to a specific state. Typically here, you can see that H is a logical high, and this is usually means that it's just connected to your VCC or your power. And the low typically means it's just an input logic low, and this is typically connected to a ground. And then you can also have arrows indicating whether you have a clocking input. And this is important to know if you want your proper operation from your chip or your component that you're using. So here we can see we have three separate truth tables. The one right here in the middle, this is the dual JK flip-flops with preset and clear. And like we mentioned, we can see these L and H's, which typically just means low and high. And here we can see our clock and then our outputs inputs J and K. And here we have our outputs Q and Q bar. So if you've taken like, it might go over this a little bit in 201, the JK flip-flops, but you'll definitely see this a lot more in 301. And if you're using your IC chips to build circuits and you just gotta check out the truth table really quick, it'll typically be found in the data sheet as well. But one important thing to know that there are different packages. This is still the dual JK flip-flops, but there are different packages, so they might be operating differently. See here, instead of us having our rising edge here, we just have little arrows indicating clock inputs. And then here on the right is just a way simpler one. It's just a 2-input positive AND gate. And same thing, high is output high, and then low. And then for B, typically when you see this X, it means that input, it doesn't matter whether that input is high or low. If one of these inputs is low, your output would definitely be low, no matter what. Next up is timing diagrams. Timing diagrams usually show how data should be sent and received from your part. They're going to show various inputs and outputs to show different logical transitions from your component. Typically, dipping down isn't, like we mentioned before, an L or a low or going to ground, and then rising or going up is typically an H, which is just the high. And on these timing diagrams, you can see different time specifications, which are indicated by arrows in between the two different transitions. So here on the right, we see that 2-input NAND gate as well again. And here we see there 4 different timing diagrams. And like we said, the behavior here when it's going down is you're typically dipping down, and you have means you're inputting from high to low. And if you're writing up here, you're going from low to high. So it might help if you're trying to see how the behavior would change for your chip itself. Okay, and then up next we have package information. For your package information, it typically provides accurate and very specific dimensions on your component. And one thing that I would say is to make sure that you have the right package, and because typically what this is used for is your like PCB layouts, and different packages can have completely different dimensions. And it's important to note that because if you're building your PCB, you would want to have the correct dimensions so that when you're connecting and soldering everything together, everything kind of fits how it's supposed to. Another thing that you might be finding here if you're looking at package information is example board layouts, like right here. This is what we have. And this is typically something that you might be seeing like on your a PCB when you print it out and stuff like that. So you would have your connection for your resistors, your capacitors here for, I guess just going into more detail, again, this is a LM741 operational amplifier. So in here, you just have the op amp. If I go back a couple slides, here's your pinout for that specific component. Just that in this case, what we're looking at here is for the board layout. So R2 would serve as if you guys are familiar with amplifiers and stuff, R2 would be serving as like your feedback resistor. R1 would be serving as your output resistor, and sorry, your inverting input resistor, and then here you have your other input, and then here's your output. So this would be pin 6 for your output, which matches what we're looking at here when we look at our pin out. So we have our pin 6 as our output, pin 1 as our offset null, pin 2 as our inverting input, 3 as our non-inverting input, and then 4 and 7 are our sorry, are our the plus and minus 15 volts to get your operational amplifier to turn on. And then we got like pin 5 is another offset null. So then that's how these connections here show. You have capacitors going in for plus and minus 15 volts just to slow down that current and whatnot. And like I said, R2 serving as your feedback resistor for your output, and then R1 serving as in the input, inverting input, and then right here we just have no resistor for it. So before we move on to any questions, I guess just to quickly show. All right, just to quickly show how you'd typically be, I guess, searching up for your data sheets. Just a quick Google search. So if you go to Google and let's say, for example, we want to search up that timer. So you just search up LM555 datasheet, you click on it, and if there's no ad showing, then you just want to click on the first link that's provided. This one here is on Texas Instruments. And just like you saw earlier in the presentation, here we have our summary page. And then you might even get a table of contents sometimes. It varies because your data sheet might be like just 3 pages, or there's some data sheets that are super extensive and you have 100 pages worth of information that just goes on and on and on. But you can see you have your pin configurations here, like we mentioned before. You have your absolute max ratings. You have your recommended operating conditions. You have all these electrical characteristics that are specific to this component. And then again, like we mentioned, you have all these graphs that can explain different characteristics which can't be so easily shown just on like a table. Yeah, so then there's just more graphs. you see, you can also, yeah, one other thing to mention, you can also get a functional block diagram, which does show how your chip would be operating. And then if we go down, as I mentioned earlier, you can get example board layouts on how it would end up looking on a PCB. And this can get more important later on when you might be making your own projects for like your design classes or something like that. Typically in regular labs, you just use a breadboard. So, but if you end up using it with like, let's say, like Eagle or something, EagleCAD or something like that, which I'm gonna show later on too, this example board layout is probably gonna be very helpful to you. So like I said, and then at the end, typically you have your package information, and you can see for different types of packages, you'll have different dimensions and characteristics, which like I said, again, are very important to know if you plan on soldering this all together on a PCB and whatnot. So this is one package here. I guess it's B0008A. And then if we move forward, you can see here that this is a different package which has its own dimensions as well. And then, so one other thing that I like to show is if here, data sheet. So we go here and again, just typically don't look at the ads, just go whichever one that you're looking for. If you're taken to, let's say, for example, this site here on Texas Instruments, some other useful features that you might find when you're searching up for your data sheets is that you can sometimes get your simulation models. So if you're using LT Spice or PSpice, it does come with its specific simulations and tools and stuff that you can use to either just use in a simulation that you're creating yourself or to just view the characteristics that you might see on a data sheet. And another important thing that might come up as well is that they do have different how do I say, packages. No. So as we mentioned before, there are different packages for specific components sometimes. And if you're looking for your EagleCAD models that you might want to use, you can if you're here on the Texas Instrument site, you just go down here to the CAD/CAE models symbols, and as we mentioned earlier, there are different packages. And this is like we saw on the data sheets, I believe, that they come with the different measurements and dimensions for your specific package that you're looking at. So you can see here that there are 3 different packages for this specific chip. But what might also be pretty useful for you is, like I said, if you are planning on using it in EagleCAD and whatnot, you can download different footprints for it here. So we have this one here for the first package that we saw. It's named PDIG, I guess. And you can see here that there's different footprints for your different packages that you might be using. But let's say your equipment doesn't come from Texas Instruments, then what you can also do is just search up your part name once again and search up Eagle. And this will lead you sometimes to Eagle libraries where you might be able to find that model that you can use in EagleCAD. So as we can see here, that there are different packages as well. But this is, once again, this is all for the same chip. And this is pretty similar to what we saw earlier on the Texas Instrument website as well. And again, if you're planning on using a SPICE model as well, you just search up your part name, SPICE model. So we can see here that it shows up on the Texas Instrument website because they do have it. So we go to a different website. We scroll down here. You can see that it does come with the SPICE model as well. So this can be helpful for components that you might not see on LT Spice or PSpice. I know a couple weeks ago I was using, I believe it was a diode, no, transistor, and it didn't come up on LT Spice. but you can just search it up and find the model here and use it in your simulations. So yeah, so that's basically all I have today to present to you on data sheets. Now we'll just open it up for any discussions if you guys have any questions.
No questions.
No questions? Yeah, I'd say yeah, I'd say they're pretty straightforward. The more you use them, the more you'll get used to them. And like I said, once you know what you're looking for in a data sheet, they'll be pretty useful to use. I know for me, example, one of the first times I found myself having to use data sheets a lot was in like EE 201, where you kind of have to, at least for me at first, having to look up pinout diagrams and stuff like that for different IC chips all the time. But yeah, there's a lot of different uses for data sheets that you can find. So yeah, that's pretty much it. Thank you everybody for attending the workshop, and anybody else who might be viewing this in the future. Thank you for attending the workshop.